Okay, this is my favorite lesson, though. I'm not even like being sarcastic, and it's not because it's crazy hard. It's because you get to like cancel stuff out, and I just get like a lot of satisfaction by like making really complex problems a lot easier. The first problem here isn't that way, so it's kind of a lame start to the lesson, but that's okay. All right, the terms at the top here. Jared, can you pay attention, please? What is going on there? Yeah, is that a printer? Oh, okay, I gotcha. I just thought it was Jared. Okay, so absolutely convergent and conditionally convergent are now on the AP test, so you have to know what they mean. So a series is called absolutely convergent if you take the absolute value and put it around it and it converges. Okay, it's called conditionally convergent if the series is not absolutely convergent, but it converges on its own. So if you put absolute values around it, it doesn't work, but without the absolute values, it works. So it's kind of like very technical. Okay, so to be absolutely convergent, does it make sense that the absolute value would work? Yeah. So if it's absolutely convergent, then it's convergent. Okay, if you put absolute values around it and it doesn't work, but it works otherwise, then that's called conditionally convergent. Okay, and this stuff we'll review again before the AP test, but maybe highlight that. There's highlighters at the middle of the table if you want to use them. Okay, so if the series of absolute values, so if this is convergent. Okay, and then conditionally convergent, if it is convergent, but not the absolute value. So questions on that at all? And then the last thing here, I already said, if the series is absolutely convergent, then it's convergent. We'll use that a lot. So this one we'll use a lot in today's lesson even. Okay, the big thing in the notes is actually on the second page. So let's get through this one so we can look at the next page here. Okay, determine whether this series is convergent. So we're going to pull from the test that we've used previously, but this one's going to be slightly different than what we did before. We're going to try this absolute values around it and see if we can prove that the absolute value of it is convergent. So let's do that. Put absolute values around it. Everything else is going to stay the same. And if we can prove that this converges, then we can prove that the original one up here converges. So that's what we're going for. What's always true about n squared? It's always positive. Does it need to be inside an absolute value then? No. So I'm going to take that out of the absolute value. So I've still got the absolute value of the cosine. So any questions so far? Okay, think about the absolute value of cosine of n, or just think about the cosine function. What is cosine always between? -1 and 1. So absolute value is always going to be what? Between 0 and 1, right? So it's always going to be less than or equal to 1 is really the important part of that, but it's really between 0 and 1. So I'm going to use the comparison test, and we're going to see what happens here. Okay, so our a sub n, if we're doing comparison test, and we're doing the comparison test on this guy here. So what is my a sub n? Absolute value, yep, of cosine of n over n squared, so it's just what's in there. And then think about what we could compare that to. 1 over n squared, good. Look at you just like jumping ahead. I like it. Okay, so looking at these two here, which one is bigger? So think about what we wrote right here. Okay, the denominator is the same, right? So if the denominator is the same in both spots, we just look at the numerator. So looking at the numerator, which one has the bigger numerator? b sub n. So b sub n is going to be larger or equal to possibly, right, which is fine. That's part of that comparison test. So questions on that part? Okay, so then what do we do for the comparison test? Good. Yeah, you're doing a limit comparison test. I know. Okay, this is the one, Lauren, where, okay, this graph, this one's bigger, right? So if this one is bigger and it converges, then doesn't the smaller one also have to converge? Okay, because it's larger than it, it's above it, right? So what we're going to do is we're going to take the series of b sub n and see if it converges. And this is where Jared was kind of going as he was jumping ahead of everybody here. Okay, if we go n equals 1 to infinity, we put b sub n in there. He says that's a p series, right? And that's a p series with p equal to 2. So what does that do if it's a p series with p equals 2? Converges. Okay, so convergent by the p series test. Let me glance here, make sure I'm not giving you misinformation. Yeah, if it's just greater than, yep. Because if it's equal to 1, it's staying constant, you know? So then it would diverge. Yeah, if it's equal to 1, it would diverge. Just 1 second. Okay, so back to this here. So if this converges by the p-series test, then what's true about a sub n? It converges. So this one here converges, right? Have we proven yet that this converges? We're almost there, right? So we're getting there. Let's go to saying that the absolute value piece here converges. So we've got this one, n equals 1 up to infinity with the absolute value around it is going to converge by what test? Just by the comparison test. So this one here converges by the comparison test. So then does this one up here converge? So think about what our new terms are up here. So what did we just show? We just showed that the original was, it's absolutely convergent. So if it's absolutely convergent, does that mean it's convergent? Yeah, that's what this one says right here, right? So because it's absolutely convergent, then we know it's convergent. That's not a test, that's just, I guess, a fact, okay? So let's go ahead and say therefore. The given series is absolutely convergent. And therefore convergent. Questions? It's really fun, right? This one's not the fun part. The next page is the fun part. So that was just our warm-up. Okay, so ratio test and the root test are the two tests we're going to do here, and they're very, very similar. So ratio test, root test are the next 2 pages. This is the fun stuff because you're going to end up canceling a lot of stuff out. If you are not canceling a lot of stuff out on the ratio test, you are probably doing something wrong and not able to solve it. So, or maybe it's not supposed to be a ratio test. Let's highlight a couple pieces here. If you look at these 3 pieces, do you see how you're doing the same thing for all 3 pieces? Okay, you take the limit as n goes to infinity, you do a sub n plus 1 over a sub n, and you do the absolute value, and then you find what that's equal to. Okay, if it equals 1, it's inconclusive. So if it's inconclusive, you have to try a different test. So that just means ratio test doesn't work. So you might have to go back to like comparison test or alternating series test or something like that. Okay, if it's greater than 1 or infinite, think about if it's greater than 1 or infinite. What do you think that that would do? Diverge, right? It's getting really big, so it's going to diverge, so it falls right into what you would think there. And if it's less than 1, then it's going to converge. So it's actually absolutely convergent because of the absolute value symbols, and therefore it's convergent. Okay, so questions on that at all? So let's try a problem here. Okay, when we're doing this, our a sub n is just what's inside of there. We're including the -1 piece this time, where with the alternating series test we didn't. So a sub n is just what's in there. Is that n cubed? Yeah. So you might try the alternating series test. If it doesn't work, then the ratio test is a really good one. Okay, when I look at that, I would go alternating series test, and I would try that one first. But now that we've learned this, if you like this better, you could try the ratio test first, and if it doesn't work, use alternating series. Chances are one or the other are going to work. Sometimes they both work, and they both give you the same conclusion. So that's kind of the nice part, is sometimes you can pick different tests to use, and they both work. Okay, but we could definitely use an alternating series test. We're going to use ratio test because it's more fun than the alternating series test. Okay, what would a sub n plus 1 be? There we go. That was really exciting. Okay, now there's a couple ways you can go about writing this, and it's up to you which way you want to do it. If you want to take the limit and keep writing the limit as you go, you can write the limit the entire way, but you have to write the limit the entire way if you're writing that it's equal. Otherwise, you can just do what's in the absolute value, clean that up, and then take the limit of what you get. So it's kind of like doing your scratch work first. It's up to you. Let's do the first one with the limit all the way through, and then the second one we'll do without. Okay, so I'm doing a sub n plus 1 on top, and then a sub n on bottom. So instead of dividing by a sub n, what could we do instead? We could multiply by the reciprocal of it, right? So let's do that instead of trying to stack all of this stuff. So a sub n plus 1 goes first. I'm going to put the -1 piece in the numerator. Let me know if you're getting lost or have any questions here. Then we multiply by the reciprocal of this one. So this is in the numerator, so it's going to end up being in the denominator. So on the top, we just have 3 to the n. And on the bottom, we've got the -1. And then the n cubed part. So any questions on that? And then we want to cancel something because we're getting excited about it, I know. Okay, it's absolute value, right? What do these -1 pieces do? It makes it negative and positive, negative, positive. Do I need them if I have absolute values? No. So it's not like they're canceling each other out, okay, but they're canceling out because of the absolute values. So we can get rid of them. So that's why if an alternating series test is not working, you would want to use this test because those -1s will cancel out because you're going to prove it's absolutely convergent. And then you can say it's convergent. And then some of this other stuff I've been kind of prepping you for. So if we're trying to get more to cancel with like these 3 to the n plus 1, we kind of talked about this already. What is this going to turn into? 3 times 3 to the n, or 3 to the n times 3 to the 1, right? If you have the same base, you add your exponents. So does that look okay to everyone? So that's what I'm going to put into that spot there. I'll just take this one step at a time. And some of this stuff might seem like, oh, I won't remember. You'll remember because you do it in practically every problem that you do. So now I can cancel out the 3 to the n power. questions so far? So this 3 that's left in the denominator, do I need an absolute value around it? Not really, right? Because it's just 3. So I can really pull the 1/3 out. It's in the denominator, so I'm going to make it a third. And even this stuff here, do I need absolute values around it if my n is going to infinity? No, because it's all positive, right? So I'm getting rid of my absolute values now for that reason. The absolute values really helped with this part here, but then I don't really need them anymore, so we can get rid of them. And this stuff here, do you see how they're both raised to the 3rd power? So you can write that as all one chunk. We've got the n plus 1 over n, all 3rd power. Questions at that spot? Cheers. Okay, now I'm going to rewrite this because it'll actually help us with the very next problem. This, I'm going to use that heart method where we split this into the 2 fractions. So we've got 1 plus 1 over n. And it's to the 3rd power. So what is that limit going to equal? 1/3, right? Because this part here is 1, and then we've got the 3rd out front. So is that greater than, less than? That's the hardest part. Less than 1. Good. So if it's less than 1, it's getting smaller. So what does that mean? It's going to be convergent. Okay? So let's go ahead and write this out correctly. So therefore, the given series is absolutely convergent. So we have those absolute values around it. And therefore convergent. By what test? The ratio test. So any questions on that? Okay, the next one over here is going to be similar, except for what do you see there, Allison, that you like so much? You see a factorial, right? And we'll get a lot quicker at actually figuring out, okay, I'm just going to split this up right away instead of doing another step. So Allison doesn't like factorials for some reason, but I'm not sure why. You don't? That's so weird. They are exciting. Okay, so let's just start by writing what our a sub n is and what our a sub n plus 1 is. So go ahead and do that, and then you can compare with what I have on the board. Whatever, that's pretty cool. Okay, any questions on what I've written up there? Okay, now this time I'm not going to write the limit until the end, so I'm just going to do the absolute value of a sub n plus 1 over a sub n. So to do that, I'm going to do this one and then multiply by the reciprocal of that one. And then multiply by the reciprocal, so we've got the n factorial on top then. Okay, I'm going to give you a minute to think about how to split that up so that we can cancel. So think about it, discuss it with somebody next to you. Okay, so he's saying some good things, but if I say it, then maybe you guys will listen. Okay, so this n plus 1 factorial, we kind of talked about it where if we had 6 factorial, isn't that 6 times 5 times 4 times 3 times 2 times 1, or 6 times 5 factorial? Okay, so you can do that where you just subtract 1 and then that's your new factorial. So if we have n plus 1 factorial, you have n plus 1, and then you take it times n, and then everything smaller than n. So that's n plus 1 times n factorial. Everyone okay with that? You might want to write yourself a little note because you will use that on your AP test. So you just got to know it. You'll use it in your homework too, so you'll remember it. Questions on that at all? Okay, so we're going to replace that piece. You could also, if you wanted to, try to split this up. It might help something. So let's see what happens. So this is n plus 1 to the n plus 1. So what's that going to split up into? So n plus 1 times n plus 1 to the n. Everyone okay with that? It's like what we did over here, right? And then I've got times n factorial. And then on the bottom, this turns into? N
plus 1 times n factorial.
Yeah, that's what we just talked about there. And then this is n to the n. And then that's the fun part because now you get to cancel. So if we cancel stuff, n plus 1s go away, then factorials go away. So really I'm just left with this. And then we can do a similar thing like what we did over here where we put the cubed parts together, only these are both to the what power? The n power. And at some point we're going to have to take the limit. Maybe we'll do it in the next step. Do I need absolute values? Not anymore really, right? So I've got n plus 1 over n to the n power. And then if we do the Hart method on that, and I'm going to write the limit here, this is going to turn into what? 1 plus 1 over n to the n. Okay, now don't try to evaluate that, okay? Does anyone know what that's equal to? Just like looking at it and like, Richard? It's not infinity, and that's okay that you thought that.
It's just 1.
It's just 1. It's somewhere between 1 and infinity. Okay, this is one of those things where the first time I taught it, I was like trying to figure out how the book got their answer, and I was like really trying to figure out how they got their answer, and I couldn't figure out how they got their answer. What you would have to do is you'd have to do where you natural log both sides, you'd pull the n down, and you'd solve it that way. So like you could get there mathematically, but we don't want to because this is going to show up on your AP test. And that takes a lot of time. So I went to Mr. A, and I was like, Mr. A, what does this equal? And he goes, E. And I was like, how did you know that? He goes, that's the definition of E. And I was like, how did you know that, though? Like, what? Why does he know that? He doesn't use that. That doesn't make, like, why do you know that, Mr. A? We use it in AP Calc BC, which we've never taught before I started teaching AP Calc BC. So why he knows that, I have no idea. But that's equal to E. So highlight that, write that it's equal to E. Usually it's going to look like this here. So it's 1 plus 1 over n to the n power, but it could look like this also. Okay, so if you take the limit as n goes to infinity, think about this for a second. What is this getting close to, the 1 over n part?
0.
It's getting close to 0. Does it ever equal 0? No. So this here is slightly bigger than 1, isn't it? But it's really, really, really close to 1. But then you're raising it to an infinite power, so it's like which infinity is going to like win out, and neither of them win out. They have to compromise at E. Questions on that? It's just E. It just is. And if we did where we natural log both sides and pulled it down and did all of that, we would get E, and we actually solved that problem earlier this year. But it's not something you're going to want to have to do on your AP test. So that's definitely something you'll have to have memorized. Okay, so now that we know it's E, we can finish it because it's what? Greater than 1. It's like 2.7 something, right? So if it's greater than 1, then we know what? It's divergent. So therefore, the given series is divergent by the ratio test. And remember, ratio means like a fraction, so that might help you Remember, because you're doing that fraction right away. Questions on that? Okay, the root test is actually really quick, so we'll get that one done here too. The root test and ratio test are pretty similar to each other. If you look at the beginning here of the root test, do you see how all of these start with the same thing again? Okay, and if it's equal to 1, what's true? Inconclusive. And if it's greater than 1, what's true? Divergent. And if it's less than 1, absolutely convergent, so therefore it's convergent, right? Okay, now here's something to note for yourself. Okay, if you do the root test and it equals 1, so that means it's inconclusive. Don't try the ratio test because it's also going to equal 1 and be inconclusive. So if you try one of these tests and it doesn't work, don't try the other test. Okay, that's what it says under here. If L equals 1 in the ratio test, don't try the root test because it's going to be 1. Same idea the other way. Okay, so if you try one of these tests, doesn't work, move to a different Bayes test. Okay, the nice thing with this is as long as you remember the very start of here, so we're going to take the limit as n goes to infinity, and we do the nth root of the absolute value of a sub n. As long as you remember that part, and you know you're going to use the ratio test a lot. The root test doesn't get used a ton, but you definitely want to know the root test. What is this whole thing raised to? The n power. So when you do the nth root, it's going to cancel that. That's like the dead giveaway that you're going to be using the root test. Okay? And as long as you know the ratio test, which you will, then the root test is pretty easy to figure out what the conclusion is because it's the same idea for the conclusion. So you just have to know this first part. Okay, so let's take and just do this part. So if we do the nth root of 2n plus 3 over 3n plus 2 raised to the n power, that's going to turn into, yeah, the 2n plus 3 over the 3n plus 2. And I don't really need absolute values because my n is going to go to infinity. So then I can do the limit as n goes to infinity of this. A lot of you will know what that equals right away. If you don't know what that equals right away, you can either divide by what? N, or you can use L'Hopital's, right? So either way, it's really quick to solve that. What's that equal to? 2/3. So if that equals 2/3, we know it's less than 1. So therefore, it's good. So therefore, the given series is convergent. And I'm just going to write convergent because we don't really need to use the absolute values here. I don't know if we can actually do that, but I don't think they take off. So the given series is convergent by the root test. Do you see how quick that one is? It wouldn't be so quick if you were trying to use the ratio test or some other test. So. Questions? Okay, so tomorrow you guys have a reality check meeting here. We've got those homework problems to do. So let's plan on Wednesday, then we can see if we have any questions. If Medford, if you guys have questions tomorrow, we can do questions tomorrow. And then on Wednesday or tomorrow, we can go over those quizzes that we had from the first 3 sets of tests that we had. And then on Thursday, we can take the quiz on these 2 sections, so 11.5 and 11.6. Questions? So quiz on Thursday.